So let's see what you did. You see my screen? Recording, Lena? So I have Lena, Aaron, Shannon, Isaac, Zach, Ryan. Oh, Aaron and Isaac, you turned in both?
Yeah. No, you know what? No. I put the worksheet on both links.
Oh, okay.
They were both active.
Okay, well, those are the only people who turned it in. Where are the rest of you guys? That would be Julia and Sam, right? What's up, Julia?
I just forgot. I'm sorry.
Okay. Let us, where was the last thing we talked about? Was there any questions on that worksheet, by the way, Lena?
No, I think everything was pretty straightforward on that.
Okay, you should have gotten all the correct answers for everything. Anybody else have a problem with anything they want to ask about?
Yeah, Aaron's saying something. Yeah. Yep. Find T H the N A. The name this one. We couldn't find the name. We didn't remember what the name of the storm that moves from the northwest to the southeast is.
Okay, so let me do a little bit today about this storm, right? So what I'm going to say here, and I'm going to make it just so here's the United States. Kind of goes down to Arizona, whatever. And then Texas does this. And then we get down here to Florida, something like that. And then we go up to Carolinas, and we go up to Maine. And then we kind of come through the Great Lakes and around to Michigan. And here's Lake Michigan. And then we have Minnesota. And then we have... Okay, there's the United States. That's not bad. Not great, but it's not bad. Okay, so if I were to show you the jet stream like this. Okay. Actually, you know what? I'm going to redraw this just so I can draw in the hole. If I said that's where the jet stream is, what are the things we should know about the jet stream? First thing is, this is the area. Well, no, what's the first thing? First thing is, this is a long wave. Right? Would you agree that the wavelength is several thousand miles across? So it is what we consider long wave. And in the long wave, this is the area with favorable divergence, right? This is where there's divergence. This is the area where there's what?
Convergence.
Convergence. Okay. So I would expect there to be weather, storms, whatever, more favorable in this area. However, what makes cyclones are short waves. Short waves are the ones that create cyclones to be born. What do we call that? What do we call the birth of a cyclone?
Cyclogenesis.
Right? Cyclogenesis. So it's in the short wave that I expect true cyclogenesis. This is the area that's very favorable for cyclogenesis. This is an area that's not so favorable for cyclogenesis. But a short wave is basically saying that the pattern embedded within this system might be a shortwave. Okay, so I've got these series of shortwaves. Now, write this down. The shorter the wave, the fastward the eastward progression of the wave. The shorter the wave, the faster the eastward progression of the wave. Okay? Which means these short waves are going to move through the long wave pattern. So these yellow waves are going to move through this wave pattern. So if I have a wave, and what part of the wave matters the most? The trough. So this trough is going to move through this pattern. So in other words, now watch this. You watching? This wave's trough is going to be like this. It's going to move like that through it. It's going to travel through it. Does that make sense what I'm saying?
Yeah.
So I'm just saying, well, what happens when the wave gets here or here? Well, in this short wave, this area is primed for divergence. This area is primed for divergence because it's downwind of this trough. But this area is divergent with the short wave and divergent with the long wave. This one is divergent with the short wave, but convergent with the long wave. So the resulting cyclone is going to be strongest here in this location. That's favorable because both the divergence and the convergent, or the divergence of both the long and the short wave, are adding together. Over here, the low is not going to be as strong because the divergence of the short wave is fighting against convergence of the long wave. Does that make sense to you?
Make sense? Yeah.
So the idea is this. Storms that form downwind of a long wave trough tend to be strong. So in this case, when I have a system like this, I tend to get surface low pressures, which we'll talk about today, and they'll move with the jet stream. And they'll kind of come up here. Those are called panhandle hookers. I know the book says hook, but the reality is they were always called hookers. And if you don't like that word, well, deal with it. Okay, because they hook up from the panhandle region. And if you recall from the geography quiz, the Oklahoma panhandle and the Texas panhandle is the panhandle region. So when we see an area of low pressure coming out of the panhandle, those storm systems tend to be big. Now, what is going on in this area of the shortwave?
It's convergence.
It is convergent, right? And what's going on in the long wave? It is also convergence. So the convergence coming out of the northwest is strong. So what that means is this low that develops is weak, but the high pressure that comes in behind it is usually very strong. Okay? Now, let's do this. I'm going to try to get rid of most of these things without destroying the United States, because I think I can. And let's imagine that I have a system that looks like this. Here's the jet stream. Here's the jet stream. Would you agree that the jet stream is kind of amplified? It's meridional, it's north and south. So disturbances associated with the short wave might come out over here. So I have areas of low pressure that develop and they move with the jet stream to the southeast. That is coming from this area near the mountains, the Canadian Rockies. This is a province called Alberta. So this is called an Alberta clipper because the low usually forms up here in Canada and it drops down. Because it's in an unfavorable region of the big jet stream, that tends to be a weaker system. So if the low comes across here, let's say that the low, and we can say this is a track of the low, so we can draw train tracks. The low is coming here, the low continues this way. That track of the low is favorable because on the north side of the jet stream, it's cold. So in the wintertime, this is usually where we get an area of snowfall. Because it's not super strong, these are usually 2 to maybe 6 inches snowfalls. These are just clippers. They build in pretty rapidly. But behind them, behind the low, we get a big area of high pressure coming in behind this, and it's strong. Which way does the air travel around an area of high pressure? Anticyclonically. So what happens is after the low moves away, we tend to get northerly winds, maybe even northeast winds, and that tends to bring in significantly colder air. So when we have these in winter, we get a little snow, and then it tends to be really cold afterward. And high pressure, so that's sunny conditions. But what happens to the low as it continues to track along the jet stream into this region? Well, now the low is in a favorable area in the long wave and the short wave. Remember, the short wave is going to be something like this, right? And so what happens is this low tends to get strong and it moves up the east coast. The winds go cyclonically around the low. And so in this area, the winds are all out of the northeast. That's why they call them nor'easters. Because the winds that are affecting and bringing the snowfall are all out of the northeast. That's why they call it that. And this can be really, really big snowstorms because this low becomes really strong. So it is not uncommon to have an Alberta clipper that rounds the base of the long wave trough and then amplifies. And it becomes this big snowstorm out east. So that's what's going on. So that's a nor'easter. Make sense?
Yeah.
Questions on that? Aaron, does that help you?
Right. Yes.
Okay, let me do this. What happens if I've got I don't have to get rid of Alberta. I don't need Alberta. I don't need the lows here, and I don't need snow in Chicago, that's for sure. Now, let's imagine that I have a jet stream that looks like this. Now I get lows that develop here, and then those lows come out of the panhandle and move up to the north. Now, the question is, where is this going to move? There's the low. What happens is when I've got a low pressure, and we're going to see this, in the area of low pressure, tends to have fronts with it, and we're going to talk about this today, that maybe look like this. Cold front and warm front. So basically, this side of it is what we call the cold sector. Over here, it's the warm sector. Okay? So if the low tracks here, what's the weather going to be like right where the question mark is? It's probably going to be warm for a while, which means it's not going to be that heavy snow. Where's the heavy snow? Almost always, the heavy snow forms in a band just, so the heavy snow is just to the northwest of the track of the low. If you want to forecast this, a typical rule of thumb is to follow the 850 0-degree isotherm. That's where your heaviest snow is. Now, it's a lot more complex than just what I'm saying, but generally speaking, if you saw a weather map and saw this, that's where you'd be thinking about it. So for us in Chicago to get a big snowstorm, we want the low to track a little bit further to the south, up like this. And then the snowfall, the heavy snow, sets up over us. So we typically are looking for a track somewhere near Terre Haute, Indiana, from maybe St. Louis, maybe a little bit south of that to Terre Haute. If we see the low tracking this way, that's when we tend to get the really big snowstorms. If it tracks further to the north, the snow gets pushed further north. And we already said that the position of the jet stream is north in the summertime and further south in the wintertime. So but that's what we go, and that all pretty much forms because in the Four Corners region, and we've got Colorado over here someplace, Texas Panhandle looks like that. Well, it's not very drawn well. Texas Panhandle, I guess that's Texas, right? But that region has the mountains, and the mountains often play a role both in Alberta, so Alberta, and then Colorado, and then in the Panhandle. So sometimes the lows form off of Colorado, maybe in Nebraska, and then they're going to track up this way. And we'll be on the warm side, or the lows are further to the south. So there's variation, but that's generally called a panhandle hooker. Those are the three main systems I want you to know. Does that make sense?
Yeah.
Questions, comments? Say something to me.
I just have a question of like what the difference between a zonal jet stream and meridional jet stream.
Meridional. Okay. So one of the things, and we're going to go to this today too, is if the jet stream is pretty flat like this, it's mostly east to west. There's not much amplitude in the waves. So will there be divergence? Yes. Will it be strong? No. A stronger divergent would be a higher amplitude wave. So this is more divergence. So when it's a higher amplitude, amplified, the systems are going to be bigger. So what we're going to show you is how does a wave go, maybe the wave looks like this today, that 2 days from now, the wave deepens. In other words, if we see the jet stream amplifying, going from zonal to meridional, I'm going to get bigger storm systems. Okay, that's what you need to do. And we haven't talked about that, but we're going to get into that. Okay, so here is a look at the models, just to give you an idea. So I'm going to use 500 millibars. That's halfway through the atmosphere, and I'm going to look at the jet stream. Now, over here, the jet stream is coming into the west. There's a trough out here, and there's a big trough here. Overall, this is a ridge. And ridges tend to be warm. The troughs tend to be cold. So I'm going to see temperatures warm in the Rockies. They're going to be much colder in the lakes. And if you don't believe me, let me show you the temperatures at 850. Do you see that there's the cold air in blue? Temperatures are down here. Much cold air across eastern half, maybe 2/3 of Canada. And where's the only place that's fairly warm? It's out in the west. So when I see the jet stream, you have to remember that the jet stream separates warm air to the south from cold air to the north. Where would I expect cyclogenesis? Cyclogenesis, at least, is more favorable out here someplace, right? So let's take a look at the pressures at the surface. I see, if I look at this, at least in this one, this is low pressure. That's where there's low pressure. This, and again, if you read the isobars, this is 1022, 1024 millibars. This is high pressure.
I would have thought that the low would be up in Canada, up in there,
Where, up in here?
a little bit to the northwest.
Well, okay, this is an old occluded low.
Oh, no,
I'm just kind of taking a look at the active ones. But now because this is tough and is going off in the Atlantic, what we really should do is look at the Atlantic and look at the jet stream here. Do you see that there's a very strong winds, strong upper level low there? And look at the surface pressure. It's really low, really strong low. Here's the one that we were talking about. Watch this as it goes off. Do you see how it goes this way? This low goes up. And do you see how it gets wrapped up? It's growing. Cyclogenesis, it's getting lower. More isobars around it. This one is really big. This is a really big low out in the Atlantic. And I'm wondering if what this is going to do. I don't know if it's going to hit England. It comes into England. That's going to be a hell of a system. Let's see the amount of precipitation in there.
why do they tend to amplify when they're riding along the coastline there?
Well, it's going through the occlusion process. So that's what we're going to get into today, okay? So that's how we're going to play this game today. But it's a big system. It's going to be very windy and very rainy. In fact, I don't think it's got snow. What are the temperatures out there? Yeah, the temperatures are in the 40s. So England, this weekend is going to be miserable. Let's do London forecast. Sunday, Saturday, rainy and windy. That's not giving you a whole lot of stuff. Because, we want to make people stupid. We can't give them actual information. We have to show them pictures because we need to make sure you're dumb. And since we treat you as dumb, we're going to give you dumb pictures. This is a bad graphic here. This is just not giving you a true picture of what's going to happen. And I was being really sarcastic, right? So let's see if there's a better description of the weather. No. I'm so embarrassed. Oh, Cubs game. All right, where were we? Oh yeah, so there we go. By the way, this is a tropical storm forecast to form. Hits into Mexico. Then let's go back to here. Let's go back to the United States. And let's go out a little bit further. So let's see what the jet stream's doing. Do you see how the trough amplifies? This thing, this trough out east. So Julia, we were kind of talking about this, right? This trough is really highly amplified. This is very cold air in here. So if I go to temperatures, you'll see that. Very cold air. Now, there is another wave, a little bit smaller, out here, and the wave is here. So I should expect pressures to fall somewhere in this region, probably down the dry line. So let's look at the surface flow there. And there is, at the surface, at lower levels, there's low, 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 low. We actually have what we call a trough. It's called a lee side trough. So here's something for you guys. Remember we talked about the leeward side and the windward side of a mountain? When the wind flows over the mountains, it tends to lower the pressures right on the other side of the mountain. That's something that we do in forecasting. And it's important that you know that, but not for this class. So there's the area of low pressure. Now let's go away. Let's go back to the jet stream and see what happens as we go out a little bit further in time. Now, look at the jet stream as we get into Monday. This wave is going away, and this wave is amplifying. So do you see that this part of the trough, I would expect there to be low pressure developing somewhere in there. Should use the correct colors. Low pressure is always in red. So the surface low pressure should be somewhere in there. Here's your surface low pressure. It's back a little bit. Let me see if I can go forward in time just a little bit. It's a little bit messy. So there's actually sort of an elongated area of low pressure. There's low pressure here, here. This is the lee side trough, and there's kind of this big, because of this wave here, this is a big area of high pressure, and that area of high pressure is making the air come this way. And so there's cold air that spills in because of this really big area of high pressure, because of that upper level wind. So we're going to stay cold in Monday. The warm air is coming off the Gulf of Mexico, right? And if we have warm, moist air, what do you expect is happening in May? It's probably going to be unstable. So here's the Cape. Notice the area of Cape is down into the warm, moist air. I just thought you should see that how thunderstorms go in there. Let's go a little bit further into time. Now the low, let's do this. The low was here. And now it starts to move up this way. Okay. Go a little bit further into time. Where does the low go? Do you agree that's sort of far south, but it's sort of a panhandle hook? Starts further south, but it definitely comes up and it goes south of us in Chicago, which means what? It means we're on the cold side of things. Air is going to come over the lake. So we get into Wednesday morning, the temperatures are not going to be warm. Where's the warm air? All the warm air is down in this region. There's the warm sector. Now it's May 12th. Am I expecting snow? Look at where the low goes. And you see how it you see how it deepens? How the low gets stronger? So it comes in here, it's wrapped up. And look at the temperatures according to this model in this area. This is middle of the day Wednesday, and all the green are temperatures in the 40s. What else do you think might be happening? It might be precipitating. So we get a big blob of rain that comes through there. Cold rain. Is there any snow in them, there hills? Yeah, look. It might be cold enough, according to the model, that there's some areas in Wisconsin, Sam, that looks like you.
God,
May 12th, and we're looking at the possibility of rain mixed with snow. I wouldn't count on this accumulating, but there's the low. So watch where it goes. Snow in the mountains in the west. And we get that system moves out. Luckily it's rain, but a little bit of snow. And look at how many isobars. Do you agree that's going to be windy? What direction of the wind's going to be? They're coming out of the north. They go around this way. So you get lake effect rain showers, little bits of showers into Illinois. So next Wednesday does not look like a pretty day. And then finally it goes past us. What comes in its place? High pressure. High pressure means sunny. And I bet you because on Thursday, it's high pressure dominating our area with very low winds. Temperatures are going to rebound pretty nicely. Now we're back up in the 60s. So even if you got snow, Sam, it's just mixing in with the rain. I wouldn't worry.
yeah, it shouldn't be on the ground for long.
So that's how the weather works. These systems that go through areas of high pressure, areas of low pressure. High pressure means good weather, low pressure means bad weather, cloudy. And what I'm happy about as a homeowner is if I look at how much rain am I supposed to get over this period. Well, notice it seems like we're still getting into this drought conditions. We've got good amounts of rain over a 10-day period or 9-day period. A lot of rain down here. And let's just hope that we get more than, at least we get 3/4 of an inch of rain. I'd like to see about 1.5 inches. Then I'd feel like we're going to come up because we're getting into a drought. Okay, so do you agree with this? So watch this, guys. That's what we're doing. Let me go to this text page and let me show you the climate page here. And here's a discussion.
What are you thinking the rest of May might look like?
I'm not thinking about anything exciting until maybe the last week of May. Here's the outlook for the next 6 to 10 days. Cold, warm to the south. And then what about if I go if I go a little bit further, it's still cold. So 2 weeks from May 3rd, right? That's May 17th. It's going to be kind of cold. What about precipitation? 6 to 10 days. See where the highest amount of above normal precipitation, right where we circle it, where all the models are generating thunderstorms. We're a little bit more than normal as far as precip. And then beyond that, we stay wet. So at least we're getting into a wetter period, but it's going to be cold. I don't see anything really good coming up. I don't see warm. We'll probably, here, just give you an idea. There's our temperature forecast. Notice in the temperature forecast, this is 60 degrees over the next several days. Temperatures hardly break 60. They get up to close to 60 tomorrow. Certainly not going to do it today. This is a bad forecast. Maybe tomorrow will be in the upper 50s to near 60. Then cooler, and then maybe touching the 60s on the weekend. By the way, what is this, guys? Review time. What do we call this? What's that? Ryan?
You mean like the wave? Is it from day and night?
Yeah, what's that called? There's a word.
I'm not sure.
Anybody? Aaron, do you know it?
She says diurnal.
Diurnal. That's the diurnal cycle. So according to one model, if you look at it, what happens to the diurnal cycle of this dark blue? It goes like this. Not much diurnal cycle. That's when the model is bringing rain and clouds. And with the clouds, we don't get that up and down. Right? We get rain coming in and then it stays up and down. So hopefully we'll get some of the higher rainfall totals. I think that's a good possibility if that storm system comes out. Now, just review. Let's go to one more thing here. And I'll go to this page. Remember the climate page for Chicago, for DuPage? Climate report, we go to DPA. What's the normal high for this time of year? 67. What did we get to yesterday? 71. So we're 4 degrees above normal. Normally it goes down to 43, and it only got down to 58 yesterday. So we are well above normal. Today, going to be well below normal. That was yesterday. By the way, how's May been so far? May has been, well, we're only a couple days in. We need to go back to this. Hold on, let's go to the monthly report for DuPage. Let's look at what April was like. The highest temperature of the month was 76. No, that's the highest record temperature. The record low is 4. So 2015, we went down to 4 degrees. A year later, we went up to 76, same day. That's crazy, huh? Our highest was on, oh, this is November. Why is this November? What the heck?
I think we lost him.
Okay, sorry, just want to have a problem, and I don't know what the problem is. So we can't do that. Let's go back to this. I can at least do this for DuPage because I can go back. So how warm was April? What am I going to look at? I'm going to look at month to date heating degree days. Normally 476. That month we had 436. So that means it was 40 degrees above normal over 30 days. So we averaged like 1.2 degrees Fahrenheit per day warmer. So April was actually warmer than normal. We had a couple of really warm days. but we had a lot of extremes. We had a little, so that's about what we had. So it's been over. What about precipitation? Since January 1st, we've had 2.97 inches of rain, 3 inches. We should be at 8.44 inches, so we're down 5.47 inches of rain. What that means is if I look here, is that we're getting into a drought. We're in a moderate drought right now. California, the Southwest, where it's hot and dry under the ridge, drought in the Dakotas. Wet down here for the most part, but it's kind of droughty. So we need a lot of rain. How much rain do we need to end the drought? Let's do this. Precipitation to end the drought. Okay. Oh, something's not working. Shoot, come on, guys. That's right. This is still experimental, so I'll leave it go for now. Okay, anyway, that's what's going on with the weather. So now we got to figure out how all these things work. So take out your notes from this unit and go to the air masses. And if I type in air masses, I'm going to get an image here. And this image is probably the best one here. So these are your basic types of air masses. Any questions on the stuff that we've just done?
Oh, no, that stuff here.
Okay. So we have 4 basic types of air mass. I suppose it would be better if I wrote with a lighter color. Those are your 4 basic types. The first letter is small. I don't know why. The second letter is capital. I don't know why. Just is. M stands for maritime. C stands for what? Aaron, you got it?
Continental.
P stands for polar, and T stands for tropical. So the first thing you need to write down is that an air mass is defined by its location of origin. An air mass is defined by its location of origin. So when I have air masses originating over waters, that's going to give me the type. So over here, it's a maritime. Over here, it's maritime. The Northern Pacific is cold water, so it's maritime polar. The Gulf of Mexico and the Caribbean is warm water, therefore it's maritime tropical. Tropical means warm. If it starts over land, I get continental tropical. So we don't have much except in the desert southwest of this continental tropical over here. We tend to get the big continental polar air masses coming down basically from Canada. So when we say continental polar, we're talking about Canadian air mass. Canadian. Sometimes if it comes in from way, and this is weird, again, I don't know why, from over the North Pole, way up north, then we call it Arctic. So an Arctic, spell it right, an Arctic air mass is the coldest type of air mass. So in this case, they call it continental Arctic. There is no maritime Arctic because if it's over water, it's not going to be that cold. So what is the definition in the notes of an air mass? Do you see that in your notes?
It says an air mass is a large area of air with similar characteristics. The most important being temperature and dew point temperature.
Okay, so it's air, a large area of air with similar characteristics, temperature and dew point, which is really a measure of moisture. Okay, now when I have a strong gradient, which is a change in something, right, over a distance of either temperature or dew point, I'm going to expect that I have a transition from one air mass to another. And that transition is known as a front. So when I have a separation of air masses, a gradient of temperature or gradient of dew point, I suspect that I probably have some sort of a front. Now, in my outline, I give you the definition of front. What does that say?
It says a front is a narrow transition zone or boundary between disparate synoptic scale air
Guys,
masses.
Go look this up. Go define this word. Disparate. Disparate. What does it say if you do a web search on that word? I need to stretch. What do you have?
Different in kind, not allowing comparison.
Different in kind. Okay. Anybody have something else different? Where did you get that, Zach?
Just from Google.
Okay. Anybody else have a different definition? I guess different in kind is not bad. Ryan, what do you have?
I got pretty much the same thing I'm saying. It's
Okay, so the way that I like to think about it is I want it to be dissimilar and separate. So I think of disparate as being dissimilar and separate. So I've got this, okay? So watch this. I'm going to go back to the models page. And I'll look at temperature. Do you agree that next week, this is not bad. Look at the temperatures down here. The temperature is 66 degrees. Then I go across here and the temperatures drop to 49 or 50. Do you agree that from here to here is a rapid change, it's a big change in temperature over a relatively small distance? That means I suspect that there is a front over here where that difference is. There is something, what are the types of fronts? What are the 4 types of fronts? Isaac?
Warm front. Cold front.
What else?
Occluded.
Okay, Sam gets this one, occluded. put that last one. What's the one in between?
Stationary.
Okay. Those are the 4 types of fronts. We're going to talk about occluded a little bit later, but I want to look at these 3 fronts: warm, cold, and stationary. How do you know which one is? So watch what I'm going to do here. I'm going to zoom in. I'm going to zoom into the planes so I can see this a little bit better. Now, do you agree that there is an area of low pressure right here and here? So it really is sort of this area of low pressure right in there. Now, it says rules for finding fronts in the notes. What's the rules for finding fronts? What's rule number 1?
Look for a strong temperature gradient.
Okay, right, that makes sense. And what's rule number 2, Ryan? Same type of thing.
Look for a strong dew point gradient.
Okay, so those are the things we talked about because we're talking about 2 disparate air masses. So where it's cold up here, I'm assuming this is continental, polar. And where it's warm, I'm going to assume maritime tropical. That's usually what we have in the central US. Warm, moist air coming off of the Gulf, cool, dry air coming in out of Canada. Do you see the way the wind barbs are? And I can even show you that with the dew point temperatures. See where the dew points are high in the blue, and then they're much drier up to the north. Okay? Rule number 3.
The front will be found in a pressure trough.
The front is found in a pressure trough. So what I'm saying to you is this, and if, again, you may not see this. I know, Kevin, you guys have a hard time. Here are the isobars here, 1,000. This is the next isobar. This is the next isobar, kind of like this. And so what I'm going to say is that I have a trough of low pressure, something like this. So that is a trough of low pressure. What's rule number 4?
For pressure change.
Not go to number 5. Skip that one for a second.
Look for a sharp change in
Okay, look for a sharp change in wind direction. Okay, do you see that the winds here are the south? Can you read that? Those wind barbs? There's south winds. See, there's, and then here they're out of the north, and they change direction right about there. That's where the winds shift. So where those winds shift, I'm suspecting that there is a front here. Do you agree, south of this front, warm air? North of this front, cold air. South of the front, for the most part, humid air. North of the front, drier air, using the dew point. Does everybody see that? Am I going too fast with you? Now, I'm going to give you a little exception to this. Do you see over here that I've got a sharp dew point, like dew point gradient? What's the dew point there? The dew point here is 64. What's the dew point here? 20. North of this front, it's 41. What the heck is this? What I have here is I've got maritime tropical air coming north off the Gulf. I've got continental polar air coming this way. Well, what kind of air is this? I like continental tropical, warm, dry air. So this, if I go to the dew point, right, I see the dew point there. Look at the temperatures. Do you see how the temperatures are warm on both sides of this thing? It's only cooler to the north of the dashed blue. So this is what I call a dry line. It is in essence a front, but it's not warm on both. It's warm on both sides, but one side's moist, one side's dry. Do you agree that it is still separating disparate air masses, warm and dry, warm and moist, cold and dry? So you could call it a front, but that's called we call it a dry line. When the distinguishing characteristic is moisture and not temperature, we don't call it a front. So over here, our main front is over here. I'm going to redraw it in here for you. So this is our main location where this is a front. What kind? What makes a warm front different from a cold front? And stationary is going to be simple to explain. What I'm going to say is, it says in there, the speed of a front. See if you can find that text in the notes. The speed of a front is determined by Julia, do you have that?
Yeah, the speed of the front is determined by the component of wind perpendicular to the front on the cold side.
Okay. So let's imagine this, okay? And I'm going to make it really, really simple. I'm going to say that this is a front. And in this front, this side is warm and this side is cold. What if the winds are from the northeast? Okay. Do you agree that this is somewhat from the east and somewhat from the north? I have the blue, just so you know, so you can have this, is the actual wind. And remember how we did with gravity and we had broke the arrow into components? This is the component perpendicular to the front. This yellow is the component parallel to the front. So I'm breaking the wind, actual wind that's out of the northeast, into its components. One component is perpendicular to the front, one component is parallel to the front. And it's this guy, the component of wind perpendicular to the front, that tells me how the front's going to move. So in this case, do you agree that the cold air is blowing toward the front? You ready? Watch this. I'm going to draw a cross section. And that cross section is going to look like this. This is the ground. This is letter A, and this is letter B, okay? What's the temperature at letter A, cold or warm?
Cold.
What's the temperature at letter B, warm? What we have in here is a front that's going to look like this. Because the cold air is advancing. Do you agree that the air is blowing from A toward the front? So the cold air pushes in. Warm air is what compared to cold? Warm air is what compared to cold air?
Less dense.
So this warm air being less dense than the cold air is going to go up. The cold air is going to wedge in underneath the warm air. The warm air has moisture, it's being lifted, and a lot of times it's unstable, and I get showers and thunderstorms. Showers, thunderstorms. And this becomes the cross section of a cold front, because the cold air is advancing. So what makes a front a cold front? The answer is cold air is advancing. Does that make sense to you guys? And cold fronts often trigger showers and thunderstorms. Not very good ones yesterday here. A little bit further west was better. But do you agree that we had showers and thunderstorms yesterday? And look at the temperature today. It's much colder. A cold front came through last night and we had showers and thunderstorms. Sam, what did you say?
I didn't get any thunder up here.
I didn't hear one. A couple of people I talked to said they heard one clap of thunder. That's it. I can just say, damn it, it's the worst thunderstorm spring ever. Brutal.
You won't get an argument from me.
So, showers, that's a symbol for shower, that's a symbol for thunderstorm. Have you noticed how much of what we've been talking about today has brought in, how many things have we talked about in the past? Density of cold air, warm air, talked about moisture, talked about lifting the air to create showers and thunderstorms. We have to know how to read the station plot. All these things we've been talking about, breaking things into components, right? The wind is the velocity vector is broken into two components. So the cold front is cold air advances. Okay, what do you think a warm front is? Julia, what do you think a warm front is?
When the warm air advances.
Okay, I want to think about this for a second. Let's do this. I'm going to take this diagram, still the same. But let's say that this warm air starts to advance. When it hits cold air, what's it going to do? It's going to go up. So what we tend to have is a front that's flatter, and this is a warm front cross section. But if you were standing here, let's imagine this. You're standing there. You're in cold air. Do you agree that you want warm air to come take its place? But what's the warm air going to do if it tries to take cold air's place? The warm air is less dense, it's going to go above it. So what I need is the opposite of cold air advancing. And the opposite of cold air advancing, even though you said is warm air advancing, is not the correct answer. So what do you think it is? Go ahead, Aaron.
C, O, cold, A, cold air, something. S, R, E, T. She says cold air retreats.
Cold air retreat. So if the opposite of advancing is retreating, and it's the cold air that determines it. That's why it says the component of the wind on the cold side. So the cold air has got to pull away from the front, and that allows the warm air to take its place. So the cold air has to retreat for it to be a warm front. If the cold air advances, then it's a cold front. Well, what do you think a stationary front is doing? It's not moving, right? So is the cold air advancing or retreating? No, it's not. So if the cold air is neither advancing nor retreating, it's stationary. The front's not moving. Makes sense. So watch this, guys. Ready? I'm going to take away these things here. And now I'm going to say, well, what would the wind have to do? Well, let's imagine the wind is doing this. The component of wind parallel to the front looks like this. Component of the wind perpendicular to the front looks like this. Do you agree that the cold air is retreating from the front, and then this moves north as a warm front? So what kind of a front is this? What do I have to do? What do I have to see?
The movement of cold air or the like wind.
I have to look at the movement of the cold air. So I've got to put winds on this thing. And I'll plot out the winds. And by doing that, I will say temperature. Okay, let me. You know what? Let me just rephrase that. So here's the front. I'm going to draw it in a neutral color of gray. I think you should see that. Here's the front. Okay, what's the cold air doing? Looks over here that this cold air is blowing this way. So what kind of a front is this? This is a cold front. And the area of low pressure is sort of like there and there. Now, I want you, I'm going to go get some water. I want you to do a web search on the following term. Norwegian cyclone model. Norwegian cyclone model. Use Wikipedia and take 3 minutes and read through that, would you please? So what did you find out? What did you find out? Talk to me about what you.
It looks like it was a almost like a cyclone theory that says that cyclones develop as they move up along a frontal boundary, and then it'll occlude as it reaches it says a barotropically cold environment.
Okay, hold on. Let me do this. Notice this was done near World War I. Are you guys, do you have any education in World War I? What do you know about World War I?
It's like 1920s.
No. 19 teens. What do you know about it? Isaac, what do you know about World War I?
I'll be honest, I really don't remember a lot about it from high school.
Did they teach you about it?
Yes, they did.
It was with like Archduke Ferdinand and his assassination. And they just all started pointing fingers at other countries of who assassinated, and it just snowballed.
Okay. Do you know any famous books from that? Do you know what they called the battle lines?
Fronts.
They call the battle lines fronts. So there was a very famous book. It's called All Quiet on the Western Front. You ever heard of that book? Aaron, have you know that
Yeah,
book?
that's what.
What big? You're terrible audio. What'd you say, Lena?
That's a good book. I've read that one.
Oh, you did? Okay, so All Quiet on the Western Front, very interesting. They've done a lot of movies. They did War Horse about World War I, where they're running in the battle. Legends of the Fall is one of my favorite movies. So they were all known as fronts. They were battlegrounds. Okay, so when the Norwegians came out, they developed this model and they started calling them fronts because that's exactly what the analogy was for these things. By the way, it says it's concentrated along two lines of convergence. The convergence line ahead of the low became known as either the steering line or the warm front, the trailing convergence zone as the squall line or cold front. So in other words, here's this thing that we drew. Here's the area of low pressure. Now in this case, it's a little bit different. This is double barrel, but this thing should be a warm front. And this one should be a cold front. So when we start drawing our models, we're going to simplify things and say this becomes a warm front and this becomes a cold front. Now, in the ones that we did, this is not a warm front, which says that this model doesn't always do things right. But it has been very good. By the way, these are the Norwegians. Do you remember any other Norwegian we talked about? From the same school? It's called the Bergen School.
Bergeron?
Bergeron Findeisen. He was from that same era. So if you want to know anything about meteorology, if you wanted to be at the cutting edge, you should have been in Norway in the 19-teens. Okay, so let's take a look at the stages of development. So the initial stages is we have a wave along a frontal boundary. So keep this open so that you have the text, and I'm just going to look at each of these diagrams. So what we have here is a system, and I'm going to draw it a little bit different than this. So I'm going to go ahead and black this out, and I'm going to say what I have here is I have this, 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 this. And in the middle, I'm going to draw this. What kind of a front is this?
Stationary.
Stationary is the blue triangles, the red half circles. That's how you write these things. Colors matter. Blue, cold fronts are always blue. The warm fronts with the little pips here are always red. Okay. Now, if this isobar is P, and keep in mind, just so you are, you're new to this, I'll forgive you if you didn't get this. That's north. This is a bird's eye view. What's this isobar? Aaron, you got something? Or the rest of you? What do you got?
P plus delta P.
Aaron, do you think it's P plus delta P?
Yes.
The rest of you? It's P minus delta P. Rule number 3 for finding fronts. What's rule number 3?
The front will be found in a pressure trough.
In a pressure trough. So that means what should the pressure do as I go toward the front? It should drop. Now, if that's P and P minus delta P, what am I drawing here?
Winds, like wind movement.
I need more specific than saying the wind.
Geostrophic wind.
It's the geostrophic wind, right? Because what would the actual wind speed be? Wouldn't the actual wind speed be slower than geostrophic and deflecting across the isobars toward lower pressure? So in this would be the actual wind. And this would be the geostrophic. Does that make sense to you? Okay, what is this isobar? By the way, do you see that here, before you do that, do you see why the winds are going from right to left? It follows the Bias-Ballot law. What's the Bias-Ballot law say?
With the wind to your back, low pressure will always be found to the left.
So the lower pressure is in the front, so the winds would have to be at your back with low pressure to your left. Okay, what's this isobar? Sam?
Which one again?
This one.
Wouldn't it be P plus delta P?
What do the rest of you think?
Would it be P minus delta delta P?
You mean P minus 2 delta P?
Yeah.
So I have somebody saying P plus delta P. Somebody saying P minus delta 2 delta P. What do you say this one is? Anybody say something different? Which one of these two is it?
I think it's plus.
Nope. What is the pressure doing as I go toward the front?
Decreasing.
Decreasing. What should the pressure do as I come away from the front?
Oh,
Increase.
increase.
It should be going back up. So watch my fingers. The pressure should drop and then come back up. Do you understand that that path I just drew is a trough? It's at the bottom of it. So this, the pressure at the front is less than P minus delta P. But it's not P minus 2 delta P because I don't have an isobar before I hit to the front. The front is the lowest pressure. Coming out of the front, the pressure starts to go up, and so it's P minus delta P. Then what's the next one?
It would just be P.
It would just be P again. Which means, which way are the winds south of the front?
Heading to the right, westerly winds.
Westerly winds, right? That would be the geostrophic. But what would the actual wind be? Slower and deflected across the isobars. Because this, we're assuming this is ground level. And if it's ground wind, friction matters. So do you agree that the actual wind would be doing what along the front?
It would be slowing it down and pulling it towards lower pressure.
And you're missing something. What would the winds be doing along the front? Julia, what do you say?
I'm not sure.
Look at the yellow arrows. What are they doing if I drew them all around here? All the yellow arrows pointing. What are they doing? Anyone else?
They'd be cycloning.
Hold that thought for now, Zach. That's not what I'm looking for, but what you have is important. What's this? If they're going this way,
Converging.
aren't they convergent? Isn't the front showing me convergence? Go back over here. He said, the theory proposed that the main inflow into a cyclone was concentrated along two lines of convergence. Right? So there'd be convergent. Now, Zach, you brought up a good point. What if I put a paddle wheel here? What would that paddle wheel do?
Spin cyclonically.
It would spin cyclonically. Now the air is not spinning cyclonically because it could be anywhere in there. But what we have is an area of cyclonic shear. You remember we talked about vertical wind shear? Just to remind you, what's vertical wind shear? What's the formula for vertical wind shear? Isaac.
That's a question.
That's a hint that I just gave you. What's the formula for vertical wind shear? Remember where this would be? Do you remember where we defined vertical wind shear? It was on the air mass thunderstorm, unit 2. So if you have that handout from the air mass thunderstorm on unit 2, or in the notes.
I have it. Do you want me to say it or no?
Yes,
Okay, it's dv over dz.
but you don't say over.
I'm sorry, dv dz.
dBdz, right? That's the question. How does the velocity change as you go up? So what would cyclonic shear be? Or what would shear? What kind of shear is this? Is this vertical shear?
It's dVdx.
Okay. So what kind of shear is that then?
Horizontal.
Horizontal.
And in this case, it would cause this to be cyclonic shear. So the front, look at the new things we just added. A front is a region of convergence. It's also a region of cyclonic shear. Cyclonic horizontal shear. Okay. Now, if I want, here's something though that you've got to pay attention to. Okay. Is everybody looking over here? Where could I have put this paddle wheel and seen it spin? Do you agree I could put the paddle wheel anywhere along the front? Right? So I just chose there. So what I need to do is I need this to be an area of low pressure that starts. What do you call an area of low pressure that starts?
Cyclogenesis.
Cyclogenesis. So if cyclogenesis is going to occur somewhere here, what do I need to kick off the cyclogenesis? I'm going here. Oh, there's an answer. I want you to write down the correct answer. What do I need to kick off or to initiate cyclogenesis? Write that down and then give me the answer exactly. You can talk to each other. I'm not going to say a word. I want to know what you think the answer is.
Would it be downwind of an upper level shortwave trough?
Oh, okay, smartass. Not only did you get a trough or downwind of a trough, and when I say smartass, you're not really smartass. You're just a smart dude. It's not just a trough. It's a shortwave trough. So what I need, the answer that I need, is the approach of an upper level shortwave trough. Because when I have that, downwind of that is where cyclogenesis is going to occur. So I didn't mean to call you smartass. I really wanted to say good job. It just came out smartass. So
No, it's all right.
at least you got it right. At least you're not I'd rather be a smartass than a dumbass. So I have to have a wave like this. So this would be the approach of a shortwave trough. And then what's going to happen is the pressures start to fall. Okay? Does that make sense to all of you? I'm going to undo this picture because I want to show you something else. So I'm going to take out the winds right here. Okay. And I'm going to take out the paddle wheel. Okay. And I'm going to remember the front is a transition zone. By the way, when I drew the front that looked like this, you notice I gave it 2 lines. So that I don't want you to think of a front as being just a single line. It's not just I'm here and then I'm there. It's a transition. So the 2 lines is telling me there's a transition. But I'm transitioning from cold air to the north. Do you agree this has got to be cold air to the north? And this is what to the south?
Warm air.
Warm air. So how do I know there's a transition zone? If you go back to the rules for finding fronts, it says look for a strong temperature gradient and a strong dew point gradient, but there was something else after that. Ryan, what does it say after that? Are you finding it, anybody?
So the rules for finding the fronts, strong temperature gradient, strong dew point gradient, and will be found at a pressure trough.
Okay, does it say someplace in there that you put the front is on the warm side of the gradient? Lena, where are you looking at that?
I think that's under number 1. It just says the front will be at the warm side of the sharpest gradient.
Okay, so if I have a strong gradient in pressure, what's true? Sam, how do I know I have a strong pressure gradient?
Strong winds.
Well, no, if I have a strong pressure gradient, I get strong winds. How do I know when I'm looking at a weather map if I have a strong pressure gradient?
Tight isobars.
Right? Tightly packed isobars. So how do I know I have a strong temperature gradient?
Tightly packed isotherms.
Tightly packed isotherms. I'm going to put them like this. So here's the isotherms. Isotherms look like this. So this might be T minus delta T and T. So they're packed over here. Now, we're going to come back to this in a little bit. When I see them packed, I put the front on the warm side of them. Okay? If I see them packed, I put the front on the warm side of them. So let me go back to this. Where am I? Let me go back to this. Do you agree that I have basically the colors are isotherms? They're packed over here. And so I would put the front like in this area. I'd put the front on the warm side of the gradient. So in other words, if this is where the front is, hold on, let me do this. I guess I can do this. If this is where the front is, over here, the temperatures are all about the same. But when I go to the cold side, the temperatures drop off rapidly. So if this is a front moving by me, It's warm, it's warm, it's warm, it's warm. Now the front goes by me, and now the temperature starts to drop off. They drop off after the front goes by. In other words, the front is on the leading edge of this new air mass. If it's cold air is advancing, it's on the leading edge. Okay, so let's do this. Put my stuff back. I get an area of low pressure. And because the pressure starts to drop, right, I'm going to draw isobars that are going to start to do this. These isobars are going to go P minus delta P, I guess, and then P. So I have low pressure in there. Do you agree that the air is going to start to circulate cyclonically? And it might cross in toward the center, remember, because it's not geostrophic. But there's air coming in here, kind of going this way. What is happening west of the low? Do you agree the air is blowing toward the front? The front had been stationary. What will it become? Do you understand what I'm asking you? You got to talk to me. I don't know what you're doing.
Just repeat what you said.
I'm sorry, Zach, what did you say?
Could you repeat what you said? I'm just.
Okay, look. The isobars were straight. And now they're going to be circled because the pressure is falling in the middle. And that creates the cyclone, right?
Mm-hmm.
And the air starts to go around in a circle. Rather than just saying it was going in two different directions like this, now it's going cyclonically, right? So over here, north of the front is colder air. What's happening over here?
The cold air is being brought into the warmer air.
Well, isn't the cold air starting to advance? So what would this stationary front become? Right? Becomes a cold front. What's the cold air doing on this side?
Retreating.
Isn't it retreating from the front? So what does this become?
Warm front.
And isn't that what we have here? Yeah, you know what? I'm not a big fan of. I can find better pictures of this. I guess maybe I can't. You would think I'd find better pictures of this. The answer is probably not. Well, here, maybe this. Does this make sense? See, for some reason, and I don't know why they do this, the low should be kind of right there on it. Right? It should be separating it. Cold front, warm front. And this is what's going on in 3 dimensions. All right, let's go back to, I guess I'm going to go back to the Wikipedia article. Because it's not, I guess it's not bad. Then what happens is the cold air starts to come southward. and the warm air kind of wraps up. So you get the cold front generally moves faster than the warm front. The cold
That
front,
would explain why it occludes.
yes, because the cold, well, yes, Sam, for what you just said, yes. The cold front generally moves faster than the warm front. Does anybody know why that is?
It's like a zipper.
No, but why does the cold front move faster than the warm front, generally speaking? Does everybody understand this picture and how we've kind of developed it? So let me draw something really, I'm going to draw it bare bones. First thing I'm going to draw is an area of low pressure. And I'm going to draw a warm front without any of the pips. And I'm going to draw a cold front like this. Isobars tend to be drawn like this. I'm going to make them as simple as possible. Okay, and they're going to go around like this. Oh, it's way bigger than I wanted it to be. Okay, so everywhere is the same pressure gradient. What I'm drawing here is what am I drawing here? What are those green arrows?
It would be like the sub, or that would be the geostrophic ones.
That would be the geostrophic wind. We're going to assume it's geostrophic just for now. In both cases, the pressure gradient is the same. Do you agree that the wind speeds would be the same? And I'm also going to say that the angle is the same. Those angles are the same. That means the component parallel to the front is the same. And it also means that the component perpendicular to the front, I kind of meant this. Oh, why does it not do the yellow? The component parallel to the front is the same. So do you understand what I'm trying to say here, guys? You have to tell me if you understand. The blues are the same. This blue arrow is pushing the cold front as fast as this blue arrow is moving away from the warm front. So the fronts in this diagram should be the same speed. Do you understand that's what I'm saying? If that were a perfect world. But the air is not geostrophic, is it? The air is across the isobars like this. What makes the air not be geostrophic? Answer that question.
Friction.
What? Say it again.
Friction.
Friction. So what does friction do? Friction makes the wind more parallel to warm front. What does it do here? More what? Friction makes the air more perpendicular to the cold front and more parallel to the warm front. In other words, what will happen then to the fronts? The cold front will move faster than the warm front because the speed of a front is determined by the component of wind perpendicular to the front on the cold side. Does that make sense to you? Give me a number. 1 to 5. Got a couple 4s.
Aaron says 5.
You're 5, Aaron. Isaac, you and Julia have 4s also. Sam, what about you, bud?
3 or 4.
I want you to spend the time going back on this diagram. So what that says is later on, what will happen here is that the cold front will end up coming down. Ooh, that's not what I wanted. Much faster like this. And the warm front looks more like this. Now in this diagram, this air over here, what can you tell me about the air in here?
It's warm.
That's the warm sector. And what's the air like over here?
All the cold sector.
That's all the cold air. Do you see how the cold air, in essence, is starting to wrap around? Once the cold air wraps all the way around, in essence, the cold front catches up to the warm front, we say that the storm occludes. We say that the storm occludes. The occlusion is where cold air wraps entirely around the warm, the low itself. Cold air wraps all the way around the low itself. Let's do this. Let's look, oops. Oh, this is not what I want. Let's go to the next picture. Cold air is now wrapped around all the way here through here. This is all cold air. The warm sector is this air down here. There's the warm air. Okay. There used to be a front, or Sam, this is what you said, zipper-like effect.
Yep.
The two fronts kind of zipper together. Notice what's the temperature here compared to here? Do you agree it's kind of cold on both sides of the front? What's the temperature here compared to here? Cold, warm. Warm, cold. Here it's cold and cold. So that purple and the triangles and the pips are on the same side. That's an occluded front. The cold air has wrapped all the way around it. Okay, now I want you to write this down. The lowest pressure of a cyclone is usually 1 to 2 days after the occlusion starts. The lowest pressure of a cyclone is 1 to 2 days after the occlusion starts. What do you think? Fair enough. Let's take a look at some examples. Let's go to our models. And I'm going to go back to the Atlantic. I want you to watch this guy here. Right there's the low. Yeah, over here, look at how strong that low gets. Where's the real warm air? The real warm air is like here. This air is where the occlusion is. So this is actually what the front is doing. Cold front, warm front. And look at how deep, how many isobars are. That is an occluded low. The low has really strengthened. Let's go back. Watch a little bit of time before that. See, it was a little bit, it wasn't that much. But notice here too, and this is kind of tough, maybe I can find another example, but do you agree that over here, the low is there, there's the warm front, and there's the cold front. So the low is just starting. There's a wave on it. I go forward in time. Over here, the low is now there. The warm front is here. The cold front is here. And then I go forward into time a little bit more. And now the low pulls up like this. The low is tracking this way and now wraps up. And that's where the low is. There's the occluded front, cold air's come around it, and the warm air's way down here into Europe. Let's see if I can look at another example in the United States. Here's the one that we looked at. Let's see if that occludes nicely. Yeah. So look at this area of low pressure. The low pressure is right there. Where's the really warm air? Like kind of in there. That's where it's really warm. The winds shift. So what I have is a cold front. I have a warped warm front. This is a little cold air damming, it's called. And then over here is a occluded front. And where's the coldest air? Coldest air is coming in behind it. Does that make sense to you guys? Do you see how these things, how this, like when I look at an area of a cyclone, I should start to expect certain weather conditions based on temperature, dew points, instability, cloud cover, etc. What do you think, guys? Does that make any sense to you?
Yeah, that makes sense to me.
Let me show you something about the low. I'm going to show you where the low tracks. The low starts here and it tracks this way. And it pulls up to the north so that in a little bit of time, watch this, that occluded low ends up being here. So the low kind of comes up and then it weakens over here. So that's the path. Do you see what's happening over here? Another area of low pressure. a new area of low pressure goes up. So I have, and this is a little bit more advanced. There's the occluded front. There's the warm air. And I get a new system. Now, what did I need to get this thing all going on together? I needed a shortwave. I don't have time to go through this with you. This is vorticity. Vorticity tells me where the wave is. So right here, this is the trough axis. Downwind of the trough is where the cyclone forms. As I go forward at a time, it comes up this way. This is a little bit later. I have the axis of the trough here where the low is. And then you see I have colors here. This is where the new low forms. So I can get systems going on and on and on and on. And that's how weather works. Now, if you really wanted to know how weather works and see these things, you have to take a forecasting course. Because you know what we do in weather forecasting? We just deal with this over and over. So Lena, that would be something that would be kind of fun for you to, especially based on your job career path, this would be something that would be interesting to you to learn how to read weather maps and then do your own forecasting.
Exactly. Yeah, I'm looking at the mesocyclone. You said there was two, so I think I'm able to take another one there.
Okay, so that occlusion that goes up and it wraps like this, and then another low forms and it wraps like this. It's like a family of tornadoes. So this happens on the mesoscale. It's a mesocyclone, which is a supercell, and it does the same thing. It wraps in cold air. It's the same thing, same processes. So if you go back and you note, you'll see that. Okay, so now before, I'm going to do one more thing and then let you go. But this is important that I show you something here. Not that one. You know. So this is what we had before. Now I'm not going to label anything because I just want to be able to draw this in here. So let's imagine this. This one is T plus delta T. If I am, and actually, you know what? I do have to label this. Let's say that's Z, and this is Z plus delta Z. If I am standing here, what's my temperature?
T.
T. What's my height?
Just above Z, so like
Just above Z. Okay. Which way, if this is upper levels, which way is the wind blowing? Parallel to the isoheights or the isobars, with lower heights, low pressure to the left. So it's a west wind. So the air right there, I am at some temperature T and some height Z, a little bit more than plus a little. Let's say 1/4 delta Z. That's where I'm at. Okay. The air is here. The air that's coming toward me is here. This air in a little bit is going to go this direction and will be here. If I stay here at the start, this is the air that I'm going to experience later. Well, what do you know about the temperature of this air?
it's the same temperature.
Same temperature. So if I'm standing there, will my temperature change? It won't. It'll be the same temperature as the wind's blowing. This is called barotropic. And barotropic, and actually, if you're going to be precise, it's called equivalent barotropic. But for this class, I don't care. You don't need to say equivalent barotropic. Sam, if you're going on to meteorology, Lena, if you decide to become a meteorology major, Zach, if you become one too. Anybody else want to do it? Going to meteorology as a major? You would need to know that. But for now, barotropic. It means that the isotherms are parallel to isobars. That's barotropic. Easy enough? Okay, let's do this. It's all right, it's gonna take me a minute here to erase all these. What if my isotherms look like this? What is the air temperature here, or at the start? Do you agree it's still T and the height is Z plus like a quarter delta Z? Just a little bit more than Z. You understand what I'm saying that? Nod or shake your head, no. Okay. What's the air that's coming at me is here. What kind of air is coming at me?
Cold air.
It's colder air, right? It's colder. It's T minus delta T. So the cold air is moving toward me. This is known as cold air advection. Abbreviated CAA if you want. Cold air advection. Cold air is coming at me. Is this atmosphere barotropic anymore? This is what we call baroclinic, where isotherms intersect isobars. And I could have said isoheights, right? Same, isoheights, isobars are basically the same thing. Fair enough? But I want you to think about what happens if I advect cold air into this point. So watch. I am here at Z plus a quarter delta Z. And now this air that's coming into this layer is getting cold. What will that do? It'll make it thinner. Thicker the warmer, thinner the colder. Which means, look at my hand right here. Watch this. This hand right here. Watch. Watch. This hand here. As the layer gets colder, this hand goes lower. In other words, will I still be at Z plus a quarter delta Z? What will happen to my height above the ground?
Lower.
It'll become lower. So what will happen is this. The heights start to fall. The isobars are no longer straight. I'm bringing cold air, which is going to make them shorter. If on the other side I had warm air advection, they're going to fall. They're going to rise. So what I'm getting is a trough. Let me erase this and show you something a little bit more simplified. So we're going to start with a wave. And I'm going to show you isotherms. Do you agree that over here, isotherms and isobars must be parallel? But they intersect here and here. What is occurring at this point? Assume that with this temperature, it's cold to the north side and warm to the south side, okay? Because that's what we expect with the poles cold and equators warm. What is occurring at this yellow circle?
Change in elevation.
No, answer my question more directly. What is occurring at the yellow circle? Everybody write down an answer. What's the answer to that question, Ryan?
I'm not sure, to be honest.
Oh,
Lena, what do you say?
Is it, this is probably totally wrong. Is it convergence?
No,
would it be cyclogenesis?
no.
Cold air advection.
Right? Isn't there cold air blowing into the trough? Because it's colder over, the wind is going this way and it's blowing cold air into the trough. What's occurring over here in this green circle?
Warmer advection.
If there's warm air blowing into the ridge, won't that become ridgier? And if there's cold air blowing into the trough, what will it become?
What trough?
Troughier. Right? You can use that word. I'm okay with it. Troughier, ridgier. So what I'm taking is the blue wave and I'm going to the purple wave. So what am I doing? What am I doing to the wave, Julia?
You're amplifying it?
I can amplify the wave. I'm going from zonal to much more meridional. I'm intensifying it. So what causes that? Baroclinity. Baroclinity, it's baroclinic. It needs to be baroclinic in order for this wave to amplify. Right? So because of the temperature advection going on aloft, I'm going to make these waves amplify. Well, here's the thing. Short waves are baroclinic. Long waves are what?
Meridiana.
Short waves are baroclinic. Short waves are the ones doing all this, and they're going to amplify. A long wave is barotropic. It's not going to do that. So baroclinity causes waves to modify. In this case, and the only case that we're going to look at is amplify. But they're modifying this because of temperature advection. Everybody good with that? Look at this now. When I, actually, let me do it this way. When I drew this thing, and I'm going to draw it really quickly, you go back to your surface. Here's your isobars. Here's your isotherms, right? Your isotherms are parallel to your isobars. We had the stationary front like this. Do you agree that the isobars and isotherms were parallel? It started out barotropic. But then, once I created the cyclone, what did I start to do? I started to create cold air coming southward, warm air going northward. We had a cold front, we had a warm front here. We had a cold front back here. The isobars were no longer like this. The isobars were now like this. And the isotherms are packed behind the front. Like this. Do you agree? Over here, isobars and isotherms are intersecting. We have cold air advection. And over here, they're intersecting. We have warm air advection. I want you to review a little bit of what I just showed you. That little part. We'll go through it again on Thursday because it's important. Do you think this is important? What do you think, Sam?
Yes,
Seems important if you're going to understand weather, doesn't it?
yes.
Okay, so watch this. I'm going to go down low. I can do temperature advection. So the pink areas here, warm advection. The area of low pressure is right there. What's behind this? Cold advection. So I have a cold front and I have a warm front. And there's the low. So what comes in behind a cold front? Cold air. What's going on ahead of a warm front? Warm air. Here's the thing you need to remember. Cold air advection means sinking air. Warm air advection means rising air. Funny thing about today is sinking air is usually going to be sunny. We have an inversion. We have fog. It's really sunny just above the ground. In fact, if I were to do this, I actually have a thin layer of clouds right there. And I have some high level cirrus clouds. Because remember, the temperature and the dew point are the same, that's cloudy. Here, they're just a little bit. So I'm so close to being a lot brighter. It's been dark all day. Look at this. Look how close we are to being sunny. Sam, you're in strata Q, but you've got a lot of
We're
broken,
starting to get some sunshine.
and we're stuck in this. You know when it's going to get clear? After sunset. And then what's the temperature going to do tonight? Crash. So if I look at our temperature forecast, here we are. Temperatures are they're not getting very warm, and they're going to crash tonight. But tomorrow's sunny, so it's going to be a big warm up. That's how I see it. So today was a lot of weather. This is where the rubber meets the road. But I hope you appreciate a couple things. Number one, look at how much stuff we had to get to before we really understood the weather. Like, I could show you this. You could learn weather stuff. I do that in my forecasting class. You don't need any experience. I can say, oh, it's cloudy, it's this. But in order to understand it, there's so much that needs to be put into it. Do you appreciate how difficult meteorology is as a science? A lot of people think, oh, it's just going on TV. And that's not even close. It's really complicated. And this is just scratching the surface of the real cool stuff that happens. But this is your freshman level. So overall, the whole thing today, overall, what's your number?
4.
4.
I've got a lot of 4s. Okay, that's good. So study this, go through the notes on the sheet, and then on Thursday, we're going to kind of review a few things and talk about some more details to try to make it more understandable. That'll take us through this week. The next week, we'll talk about thunderstorms a little bit, and hurricanes a little bit, and fun stuff like that. Okay? So take a good set of notes, and I will see you guys on Thursday. Nice
All right.
job today. You did a good job. Jill, you going to be on class on Thursday?
Yeah.
Good. I will see you guys then. Bye.
All right. Have a good one.
Thank you.
Have a good day.